Okay, so I was saying, let's continue from where we had ended yesterday. Okay. So from there, after we are done with we just want to do some maybe 2 examples so that we were able to remember and we can move on to different parts, which is equilibrium to do with solubility, constants, and solubility calculations, as well as the introduction to the very subtopic under chemical equilibrium. So you guys said we ended on question 5, so ended yesterday. Okay. So question 6. Okay, question 6. At a particular temperature, 12 moles of SO3 is pressed into a 3 liters rigid container, and the SO3 dissociates by the reaction. So we've been given the reaction, we've been given the equation, we've been given the information of the initial concentration of the material that was decomposing. Okay. So now, how do we get to calculate K in such a case? Okay, so if you look, pay particular attention to this question, you notice that the information that has been given is a bit different from some other questions, because the other questions will give you the concentration there and then, but in this one, we've not been given the concentration. We've just been given the information that will help us to determine the initial concentration of what? Of the reactant. Okay. So let me just copy this very question just there. Okay. So that's the question that we have at hand. What are we supposed to do? So at a particular temperature, of course, we've been given 12 moles, the SO3. And then we've been given the size of the container to be 3 liters. So we have our equation there. So then the question continues to say at equilibrium. So we've been given the concentration at equilibrium as well, 3 moles as well. But that's not the concentration. We need to take it to the concentration. So before we can even come up with our ice table, we have to first of all determine what? Determine the concentration. So first of all, let's start with the initial concentration. That was 12 moles. So we all know that for us to calculate the concentration, we're supposed to divide the number of moles by what? By the volume. Okay. So in this case, the number of moles are given to be 12 for the initial concentration of the SO3, divided by the volume, which was given to be 3 liters. Okay. So that is in moles, then this is in liters. So if you divide, you are going to have what? 4 molar. So what is our initial concentration? Okay. Are we together? So equally, if we are to determine the final concentration of SO2, sulfur dioxide, we're going to find that we're going to divide the 3 moles by the 3 liters, because it's the same container, of course, and the term rigid means it's not changing. So we expect to be 1 molar in terms of the final concentration. That is at equilibrium. Excuse me. So we can come up with our ice table now, so that we're able to make some computations and there. Okay. So I can create some space now. So don't forget, our initial concentration has been determined to be 4 molar. Okay. Okay, so here we are. Right. Okay, so our ice table is supposed to represent the reactants and the products that we have in this case. Okay. So if you look closely, we are supposed to write first of all the equation that we have, or what I can do, I think you can just copy it down here. So we have 2SO3. That is our reactant. That's the only reactant that we have in this case. Okay. Then in terms of our products, we have got sulfur dioxide. So don't forget that we have 4 molar there. So just create some space. So continue writing my equation. So don't forget we have the 4 molar there by our initial concentration. So plus, what do we have? Well, we have oxygen gas. So I've divided by 3, denote the states because they're in the same, it's an homogeneous type of equilibrium because they are all in the same phase, which is gaseous states. All right. So what are we supposed to do? I said we're supposed to come up with the ice table, which implies that we're supposed to indicate our initial concentration, the change, and the equilibrium concentrations. Okay, we'll come up with variables that are going to help us to, get to calculate the casing. So this is supposed to be a table. Okay. So we have our table here. And this should be separated as well. I should be separated like that. Okay, so don't mind the way we've drawn the table, but yeah, it's supposed to come up with the table. Okay, so what are we supposed to do? We are supposed to write the information that has been given, first of all. So initially, we've been given the 3 liters. We've been given 12 moles dissolved in 3 liters. So we determined the initial concentration to be 4 molar. So we're supposed to indicate it for SO3 to be, so let me use a different color so that we're able to distinguish. So it's been given 4 molar, the concentration. Then since this reaction was just starting, we didn't have any products. So therefore, on the other side, we were just supposed to indicate 0 concentration. Okay? Because when you are starting with a reaction, you don't start with any products, you just start with what? Just start with the reactants. So we don't expect to have any concentrations unless the question tells you so. Okay. So what else have we been given? We've also been given at the equilibrium concentration for what? For the sulfur dioxide to be 3 moles. So that being our initial, if you take the moles to concentration, you're supposed to divide the moles by the liters. So if you divide 3 moles by the 3 liters, just going to have what? A 1. So that is for sulfur dioxide. So indicate it in this column to be 1 molar as our final concentration. So that was the information that we are given in the question. Do we have any concerns before we move on? Okay, so if at all you don't have any questions, it's time now to indicate the changes that we should expect to occur. So we are supposed to indicate in terms of the stoichiometric coefficients of both the reactants and the products. So in terms of the reactants, they're supposed to be negative. Then for the products, they're supposed to be positive. Why negatives for the reactants? Because we expect the reactants to reduce as the reaction progresses. And for the other side, which deals with the products, we expect them to increase. So we expect, first of all, the 4 molar concentration to reduce, then we expect the 0 molar concentrations to increase because this reaction is progressing, favoring the right-hand side, which is the products. So therefore, we're going to introduce a variable of which the most common we'll use one is x. So in terms of the reactants, it's supposed to be negative 2x, just like I said, the stoichiometric coefficient should be indicated, and for the reactants, it's supposed to be negative. Then when you look at the products, here we have got sulfur dioxide, supposed to be positive 2x. Then on the oxygen gas, it does a stoichiometric coefficient of 1. So you just expect it to be positive x because it's also what? A product. Do you have any questions? Okay, so no questions. So for the equilibrium concentration, we just have to subtract the change, or just have to add the change to the initial concentration. So adding 4 and negative 2 will just be 4 minus 2x. Okay. Then for the other parts, it will just be 0 plus x, which will just be x. Except for the sulfur dioxide, we are not indicating anything because it was already what? It was already given to be 1 molar concentration. Okay. Any questions? Any concerns?
No.
All right. So if there are no questions, let's create some space on top there. So, okay. So I want to find the K constant, right? So our first goal here is to find the value of x. And we can try to check for the column which has got 2 like terms. So in this case, we've got the middle column here as all what? Has got the initial concentration and the equilibrium concentration. So therefore, if we are to add the initial one, which was 0 plus the change 2x being equated to the final, which is 1, what do we expect? We expect our x to be equal to 1 divided by 2, which will just be 0.5. So we have 0.5 there for x. So we can determine the equilibrium concentrations for the other two by just substituting the value of x here. So if you look at the first one, which of course we know is SO3, where there is x here, we put 0.5. Okay, are we together? Okay, so we can just find the equilibrium concentrations directly by substituting in this last column. 4 minus 2x, that will give us the initial the equilibrium concentration. So we have the 4 minus 2, then our x is 0.5. So 0.5 multiplied by 2 will just be a 1, and 4 minus the 1 will just be 3. So that's the molar concentration for the SO3 at equilibrium. So expect it to be 3 molar of concentration. Moving on to the last part, what do we expect to be our concentration? You just expect it to be equivalent to x because we just have x here. So therefore it's going to be 0.5 molar concentration. Okay. So if you go back to the question, what was the question asking? The question was asking us to find the equilibrium constants. Okay. So we've just determined the equilibrium concentration. Therefore, we're supposed to determine our formula from the question that we've been given. And if you go back to the equation, what was the equation? What was the equation? So the equation was SO3 giving us sulfur dioxide plus the oxygen gas. And the equilibrium concentration K is supposed to be determined by dividing what? By dividing the products by the reactants, of course, raised to their stoichiometric coefficients. So let's write that expression on top here. So this other information is no longer needed because we've already found the equilibrium concentrations. Okay. Do we have any concerns, any questions? So we know our K, expression for our K is supposed to be the products where we add sulfur dioxide. It had the stoichiometric coefficient of 2 being multiplied by what? The oxygen gas over the SO3, which also had the stoichiometric coefficient of 2. So from there, our Kc is going to be equal to what? Sulfur dioxide. So sulfur dioxide, we add what? We add the 1 at final concentration. So 1 squared multiplied by the oxygen, or 0.5, divided by the SO3, which is 3 squared. So 1 squared is just 1. 1 by 0.5 will just be 0.5. So we have 0.5 as our numerator. Then for our denominator, it will just be a 9. So if you are to divide that, what are we going to have? So 0.5 divided by 9 will give us 0.055. So it just be 0.06. Okay, so therefore our Kc is equal to 0.
Sir, there's a question.
Sure. Yes, you can go ahead.
Is it 9 or 27?
Which part?
There on KC.
Oh, it's 3 squared. Have I answered the question?
Yes, sir.
All right, so we've determined our K for that question. Any other questions before we move on to the other parts? Okay, so I think the revision under the chemical equilibrium is enough. We've done the ice table for this question. We also did some other questions the other day. Okay. So you guys can move. I'll send, of course, I'll send the answers to the group for question 7. It's also focusing on the ice table. So just like I said you're supposed to care of when you're given a question. Make sure you have what? You have the information that you've been given converted to the concentration, right? So like if you look at the 2 moles, like in this question 7, 2 moles, then 2 liters. You're supposed to convert the moles to the concentration, which will be the moles divided by the liters, which will just give you 1 molar concentration. So but you consider that now to be what? Your initial concentration for that given reactant. Okay, I think we can answer question 8 because it looks to be a bit different. Yes?
Sir, can you tell the person with the background to mute the mic? It's disabled.
All right. So question 8, I guess. Question 8 is a bit different from the ice table because there's an addition of calculating what? The Kp. So let me just give you a guideline on how to go about this question, or of course even just solve it. So this question has given us the equilibrium concentrations already. Okay, as we can see, the equilibrium concentrations have been given for the reactants and the products. Then we're asked to calculate Kp. Okay, let me copy this question to the board so that we can do it as soon as possible. Save on time. Right. So okay, so at 3.7 degrees Celsius, the equilibrium concentrations has been given. Okay, so we have our equation there. Now I want to calculate what? Our Kp at this temperature. So what do we do? First of all, from the information that we've been given the concentrations. So for us to find Kp, we would rather first of all find Kc, because we've not been given the pressure. So it's better we find the Kc, then we'll be able to convert the Kc to Kp as well. So of course we know our equilibrium concentration in terms of our K expression in terms of concentration is supposed to be. So in this case, it would be our Kc will be given by, if you look at the products that we have in this case, what are our products? We have got carbon monoxide raised to its stoichiometric coefficient of 1, then by the hydrogen gas, which has got a stoichiometric coefficient of about 2. So it will be 2 squared. Okay, divide by what? We're supposed to divide by the reactants. Okay, so I believe we are all aware of that. We know how to write that. That's just about the K expression. So if you look at the concentration of carbon monoxide, it has been given to be what? It has been given to be 0.24. So I can substitute that there. So we have 0.24. Then for the hydrogen gas has been given to be what? It's been given to be 1.1. Then for the CH3, that's methyl. That should be methyl, if I'm not mistaken. So that's been given to be or ethanol, sorry, has been given to be 0.15 there. 0.15. Okay, so we just have to calculate that. So 1.1 squared is what? Is 1.21 multiplied by 0.24 divided by 0.15. So therefore our Kc is going to be equal to 1.936 1.936. Okay. So what is our Kc? I believe we all know how to do that. So now, this question is not interested in the Kc, it's interested in the Kp. So what do we do? So we know we have 1.936. So what do we do there? So we say the relationship that lies between our KP and KC, but KP is given by KC multiplied by the rate gas constant multiplied by the temperature raised to the change in the number of moles. Okay? So
Yes,
what is
sir.
our, pardon? So we have 1.936 multiplied by what? Multiplied by our rate gas constant, which in this case is going to be 0.08, should be 21 there, times our temperature is not going to be in degrees Celsius, it's supposed to be converted to Kelvins. So 327 plus 273. So you get your temperature to be equal to 600 Kelvin after the addition. For the change in number of moles, you go to equation, look at the stoichiometric coefficients. This one has got a 1, this one has a 1, that one has a 2. So 2 plus 1, on the product side you have 3, on the reactant side you just have a 1. So the change is what? 3 subtract the 1, which will give us what? Which will give us a 2. Then get your calculator, multiply the 600 by 0.0821, square it, multiply the 1.936. So your answer is going to be equal to, let me even pick a different color.
Sir,
Yes,
sir, I have a question.
sure. You can go
How
ahead.
did you find the 2 on the change? How did you find the 2? The square root of the what's this? The 2 there.
I've even lost the board. Okay, let me just look at. So I said the stoichiometric summation on the right hand side was 3, right? If you look at this equation,
Yeah.
where is that equation? This one, right? So this one has the carbon monoxide has got a 1 there. So 1 plus a 2 will give us what? A 3.
3.
Then on this other side,
-4.
we have a 1.
Yes, sir.
So to subtract the 3 by the 1, that will give us a 2.
Okay, sir. Thank you.
Okay. Okay. So I've lost a board. Let me try to retrieve it. So you write your answer to be 4,697.8. That would be your KP. Okay. So I believe that's are there any other questions?
No.
No, wait. The temperature is supposed to be in Kelvin.
Yes, supposed to be in Kelvin. I'm trying to retrieve. So when the meeting stops, just rejoin. Okay. So which part is that one? Okay, so no, it's gone. Okay, you can go to a different question. And we just have about 30 minutes before the meeting ends. Okay. So I think enough about the chemical equilibrium part. This question is just the same as well. It applies the same concept. So we're going to start from question 10. Okay. We're now trying to cover the parts for the solubility equilibrium. Okay. So just before we even get to these questions in this story sheet, I found a worksheet that can help us to revise this very topic. Okay. So there are two terms that we need to be familiar with under this part for solubility, which is we need to be able to define what solubility is all about. That's a very important point. Okay, solubility first of all. Of course, we know what solubility is all about. We talk about dissolving something. Okay, now chemically speaking, we would say solubility is the concentration of products or reactants that must be dissolved in order to make a saturated solution. So there's a new term that we've come across now, saturated solution as well.
Sir,
hello?
can you share the paper?
You're unable to see. Okay, so the meeting has almost expired. Just rejoin. Then I'll share the screen. Okay?
Okay.